Share screen. Oh shit, I'm having some internet problems. Okay, can you guys see that?
Yep.
All right, great. Solve my internet problems. Okay, folks, so let's see. The plan for today is to continue our discussion of WKB, and also to introduce a new topic, which is the Dirac equation. So let's start with our WKB discussion. And for the WKB discussion, we're going to talk about alpha decay. That's the plan for today, alpha decay. And so to begin, let's remind ourselves what WKB even is. And so for WKB, it's an approximation technique that we described before, but there's two main results. And so I'll remind you the two main results which we derived. And the first main result is with bound states. And for bound states, we have this kind of a situation where we have some bumpy potential, and that's what our potential looks like, V of x. Let's just say 0, and let's just say x equals a. And let's suppose that our energy is here. And then what we found is that from WKB tells us that the integral from 0 to a of this function k of x dx is quantized. So it's basically the number of waves is quantized that we can fit into the well, where k of x is defined as this function 2me minus v of x. It's basically a spatially dependent wave vector. That's how you can interpret it. Sort of like 2 pi over lambda of x. It's a spatially dependent wave vector. And so this gives us a constraint on the eigenstates. This is a constraint on the eigenstates. So you can get the eigenstates by solving that integral. All right, so that's pretty useful. But then also, even more useful, to be quite honest, is the tunneling result. This is the more famous result, the tunneling result. And the tunneling result is more for this kind of situation, where we have some bumpy barrier. And that's our V of x. And we have our energy here. And so this is tunneling. And this I'll call this x1, I'll call this x2. And for this kind of situation, then we see that the transmission coefficient is this. T of E is equal to e to the negative 2 x1 to x2 kappa of x dx, where kappa of x is the decaying constant, the decaying the decay constant. Kappa of x is equal to square root of 2m v of x minus e over h bar. Okay, and those are the two most famous results of WKB. And so what we're going to do today, we're going to do the tunneling, the most famous tunneling example, which is alpha decay. And this is a very famous result that came from WKB. And this is really the first theoretical nuclear physics result. Nuclear physics result. And let's see, who did it? It was done by a guy named Gamow. I don't know how to pronounce that correctly. In 1928. And so let's talk about alpha decay. All right, so that's what we're going to talk about now. And so alpha decay is what happens when you have a nucleus. So here's a nucleus. Let me draw a bigger nucleus. Here's a nucleus. All right, and the nucleus is inside of the atom. And so the way to think about it is that we have, there's an alpha particle bouncing around inside of the nucleus. Inside. Can somebody tell me what an alpha particle is?
It's a helium nucleus.
Right. And what is it made out of?
2 protons and 2 neutrons.
Exactly. Thank you. Helium nucleus equals 2 protons and 2 neutrons. So this thing is bouncing around. P, N. So we think of this as like a particle, and it's just bouncing around. It has some velocity, and it's just going boink, boink, boink. It's just bouncing around inside. And so, but then every now and then, it comes out. So it bounces inside, but then every now and then it pops out. Pops out occasionally. And what do we call it when it pops out? What's that called? Has a name. Little particle is bouncing around, then it pops out. What is it called when the little particle pops out?
Is that just decay?
Yeah, that's alpha decay. That is called alpha decay, that's right. But it's also radiation. This is the source of radioactivity. That's what radioactivity is. Stuff bouncing around and popping out. So that's radioactivity, or one form at least of radioactivity, an important form. So that's radioactivity. And so so what the old folks noticed, like a long time ago, 100 years ago, people noticed that there's a lifetime. The alpha decay can be described by a lifetime, and higher and the alpha particles have an energy when they pop out, and it turns out that higher energy particles have a shorter lifetime. And this is something that the old timers noticed, but they could not explain it. They had no way of understanding it. And so what they did was, to explain this type of phenomena, they used this kind of idea. They came up with this model, and Gamow came up with it, but I don't know who else worked on it. But I know Gamow worked on it. And so the idea, the simple idea, the trivial idea is that we think of the nucleus as a box. You know, I'm not the only one who likes particle in a box. And so this is the nucleus. And so let's call this 0, and let's call this r. So that's the radius of the nucleus. Radius of nucleus. And the idea is that the alpha particle is just bouncing around inside of a box. All right, and so it's just particle in a box. Particle in box. Alpha. But then every now and then the particle gets out. So how does that work? So what they hypothesized is that the hypothesis was that there's some hypothesis, strong nuclear force. So the depth of the box is the strong nuclear force. And you guys, all your life, you've heard how strong the nuclear force is. That's how come we can have nuclear bombs that blow up cities, because of the strong nuclear force. And this is the origin of the, or this is that force. So the depth of this well is the strong nuclear force. So the idea is that there's this strong attractive force that's holding them together, and it's really strong, and that's a really deep well. So that's the nuclear force. But every now and then something can get out. So how the hell does it get out? Well, the idea is that it tunnels out. It tunnels out of the box. So this is the hypothesis of the potential. So people hypothesize that a nucleus looks like this. I have the box, and this is it's spherically symmetric. So let's just do spherical coordinates. So this is the radial coordinate. So that's 0. And the idea is that it has some radius r. Now, the thing is that I got this. So let's think of it like this. I got my nucleus, which has, let's think of it as having Z protons plus 1 alpha particle. And then there's the alpha particle, alpha. So we think of the nucleus as having a bunch of protons and neutrons all squished together, and then let's just think of that alpha particle as extra bouncing around, and that every now and then the alpha particle can escape. So if the alpha particle escapes, then the situation goes like this. I still got my nucleus left behind with Z protons, and each of the protons has charge plus E, right? But then I got my alpha particle, P, N, N, flying away. But notice that the alpha particle has Z equals what? What's the charge of the alpha particle?
2.
Right. So if the alpha particle can get out, so here the alpha is attracted, right? It's inside the nucleus, and so it feels a strong attractive force. But the moment it gets outside of the nucleus, what does the alpha particle feel? Tell me.
Repulsion.
Right, because it's positively charged and the nucleus is positively charged. So as soon as it gets outside, boom, it gets pushed away very hard. So then it's repelled. Alpha is repelled. And so this simple concept, you can write it out in terms of a potential, because here, now let's go back to this potential that I'm drawing. I have this deep attractive potential. And then, but then as soon as I get out, so here, let's put 0 here. This is 0. And so it's it's a deep attractive potential. I'll call that potential, whatever, I'll just give it some, I'll call it, V naught, some very deep attractive potential. But then as soon as I get out, my potential looks like what? What is the shape of my potential as soon as I get out? And I'll call this R1. So this is the radius of the nucleus, radius of nucleus. And what is the force once I get out? What is the shape of it, the potential?
It's like Coulombic.
Exactly, it's Coulombic. 1 over R. And so now let's assume that my particle has some energy, and the energy has to be above 0. So that's my energy of my particle. That's the energy of the alpha particle. Energy of alpha particle. And then let's draw this, let's call this point R2. And so you see that this is the Coulomb potential. But that creates a tunnel barrier. So it's kind of funny. It's like the Coulomb potential, which is really actually repulsive, in this case is sort of keeping the particle inside. You see that? So the particle at this energy is bouncing around inside, and it hits that Coulomb potential, and it stays inside. And so the way to think about it is that the particle, think of it like this: the particle has some velocity. Actually, I won't draw it down there. Think of it like this: the particle has some velocity, v, and so it's bouncing around inside, back and forth, and so the particle bounces. And it has some velocity, and so what is the time between bounces? Delta t per bounce equals what? Somebody tell me. The particle, let's say that inside the alpha particle is bouncing around inside the nucleus with some velocity v. What is the time between bounces? How often does it hit the side of the confining potential, that Coulomb potential? Tell me.
R over V.
That's exactly right. But let's call it a 2R1 over V. Exactly. The distance, which is twice the radius, the diameter, divided by the velocity. That's exactly right. And so that means that the frequency of bounces is equal to what?
V over 2R1.
Exactly. And that means that the probability per bounce, let's just say that the probability to escape per bounce is equal to gamma. Let's say the probability to escape for 1 bounce is gamma. So that means that the probability per time, so then let's assume that we start with all the probability inside, but then as time, so that's at t equals 0, but then at t greater than 0, our probability starts to leave, and we start getting probability outside. This is probability. Probability less than 1. And this is growing. And so we're going to get some probability per time. The probability is going to get out right? I'm using this probability language like we used for time-dependent perturbation theory. So we have this probabilities leaving the nucleus. And so if the probability per bounce is gamma, that's the probability to escape. What is the probability per time that's leaving the nucleus? Can you tell me? It's sitting right there on the page.
Is it the probability that it will leave over that time?
Oh, yeah, that's exactly right. That's exactly right. You can think of it as gamma over delta t. Or you can think of it as gamma times the frequency. Because think of it like this. Suppose that I'm bouncing 10 times per second. And so, and suppose that every time I bounce, my probability of escaping is 1/100th. And I'm bouncing 10 times per second. And every time I bounce, I have a 1/100th probability of escaping. That means the probability per time is 10 times 1/100th is 1/10. 1/10 per second. Do you see what I'm saying? Because that's like the probability of escaping. So the probability per time for the probability to sort of leave is going to be the probability per time is equal to the probability per time is equal to what did I say? Frequency is going to be V over 2R1 times gamma. And by the same token, so that's equal to the rate of escaping, right? And but then also notice that I have a lifetime, and the lifetime is just equal to 1 over the rate. That's the characteristic time associated with this. The lifetime is the inverse of the rate, and so the lifetime of the particle will be equal to 2R1 over V times gamma negative 1. Okay, so that's the lifetime of an alpha particle. And so, yeah.
So I guess like, what does lifetime really mean in this sense then? Is it just like a measure of the rate?
Yeah, because the rate is equal to probability per time. And so if I invert that, then I'm going to get, let's say that I'll call this delta P over delta T. And if I invert that rate inverse, then that's going to be delta T. I can think of that as delta T, and if I divide it by delta P over 1, I can think of it as like, this is the time it will take the full probability to escape. Do you sort of see that? So it's sort of, because it's like time, you know, it's like time over probability. But then if I divide it correctly, then the denominator is 1. And so I can think of it like, you know, seconds per 1 probability. So it's basically the time it takes for all the probability to leave. And that's a lifetime. So that's a way of thinking about it. Okay, so you see then, like if we want to calculate the lifetime, then what we need is this gamma factor. That's the most important thing. So let's just call this prefactor just some constant that we're not going to worry about. It turns out that this part is not too important. The radius of the nucleus divided by that internal velocity, that turns out not to be such a big deal. It's really this this factor that's the most important one, this gamma factor. And so let's find that. And so let's notice that gamma is equal to the probability to escape for one bounce. Probability to escape per bounce. And this is the situation that we're in. We're living inside this funny potential like this. So this is 0, this is V, this is E. So what is another word for this quantity gamma? How do I think of this gamma quantity in quantum mechanics? What is it in quantum mechanics? The probability to escape per bounce. So the little alpha's going boing, 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 hitting that wall, and every time it hits that wall, it has a chance, a probability to escape. In the language of quantum mechanics, we have a special word for that probability to escape per bounce, and we call it what?
Tunneling?
It is tunneling. The process is tunneling, but that probability to escape per bounce itself has a special name. What is it?
Transmission probability?
Say it again.
Transmission probability?
That's it.
Or no?
It has a name. We call it the transmission coefficient. And you guys have calculated it a million times. That is the transmission coefficient that you guys have calculated last semester. The transmission coefficient. That's what it is. That's exactly what it is. That's what the transmission coefficient is. It's a probability to get through a barrier. If you hit it, boing, probability to escape per bounce. And so we know how to calculate it because look, we have these two distances. I got a V of R here, and I got a distance here, which is R1, and I got another distance here, which is R2. And if I know this, if I knew the functional form of that V of R, then I know that the transmission coefficient, gamma, is equal to what? And I'll give you a hint. Use WKB. What is gamma?
E to the -2 times integral of R. I guess in this case, would it be R1 to R2?
Yes.
And then kappa x dx.
That's exactly right. Where kappa of x is equal to what? Where kappa of x is equal to what?
Square root of 2m, and then in parentheses v minus e over h bar.
Exactly. Good. And so now the next question is, what is V? Somebody tell me, what is V?
It would just be the charges multiplied together divided by 4 pi epsilon r.
Exactly. And we got the nucleus here, which has ZE, and then we got the alpha particle here, which has how many? What's the charge of the alpha particle? What's the charge of the alpha?
2e.
Right. And so in the coefficient, I have ZE times 2e, exactly what he said, 4 pi epsilon naught r. That's it. Pretty simple. And these R1 and R2 are, notice that R1 and R2 are special because those are the points where the energy and the potential are the same. And what are those points called again? We talked about them last time. What are they called?
Turning points?
Classical turning points, right? Because that's where classically, that's where you would turn around. That's right. And so R1 is not obvious what it is. You know, R1 So we need, okay, so the only things that we're missing, so basically we have everything we need, but the only things we need is R1 and R2, right? Everything is known except for R1 and R2. So R1 is the radius of the nucleus. And we don't know that. So we'll just call that unknown factor. All we know is that it's really small. It's really, really small. R2 though, how do we get R2? We can find R2. We know R2. How do we get R2?
Just set the energy equal to the V of R.
Exactly. Set energy equal to ZE 2ZE squared over 4 pi epsilon naught R2. And then we can find that R2 is equal to 2ZE squared over 4 pi epsilon naught E. Okay, so we do know R2 because the assumption is that E is known. E is we're taking as a given. Okay, so we know R2. So then all we got to do then is to calculate. So then we just have a math problem. So we see then that gamma is equal to I can just plug it all in, and it's going to be gamma. Let me just make sure that I did this. I just want to make sure that okay. All right, I sort of used unfortunate notation here, but this is okay. And so we see that gamma is going to equal e to the -2 times 1 over h bar, R1 to R2, square root of 2m v is 2ze squared over 4 pi epsilon naught r, 4 pi epsilon naught r, minus e dr. Okay, you see that? So that's our that is our transmission coefficient. Is that that integral? And so then what we have to do then is we have to do that integral. And so it turns out that this integral, if you do that integral, then you see that it's equal to e to the -2. So we have to do that integral. And so then that integral is a little bit tricky, but I'm not going to go through the details, but it's, well, you can very quickly, you can see that it's equal to square root of 2me over h bar times r1 to r2 square root of r2 over r1 minus 1 dr. It's a famous integral because lots of people have solved it. And so you can solve using a change of variables. You can do a change of variables, which I'm not going to do. I'm not going to go through all the tedious algebra of it. I'll just tell you the change of variables, sine squared u equals r over r2. And when you do that change of variables, then you see that this thing is equal to it's going to be equal to square root of 2me over h bar times pi over 2 R2 minus 2 square root of R1, R2. Okay, it's approximate. And so then what we're going to have is, if we say that R2 is way bigger than R1, then what happens is we can knock out this part. And so then we get that gamma is equal to e to the negative 2 square root of 2me over h bar times pi over 2 R2. Okay, and then we use the fact that R2 is equal to 2z e squared over 4 pi epsilon naught e. And you plug that in, and then you can see how this gamma is going to equal e. Now I'll just write it like this, to the negative some constant a times, and what's the energy dependence here? In the exponent? Can you see the energy dependence in the exponent?
Is the 2me, is the e under the square root or not?
Yeah, it is. Can you see the energy dependence?
Yeah, it'd be like to the square root of e, right? It'd cancel out.
Well, it's going to be square root of e over e is equal to 1 over square root of e. See that? And so here it's going to be times 1 over square root of e. And so then and so this is the rate, the rate of escapes, the rate of alpha escapes, and so then the lifetime is equal to 1 over the rate is proportional to e to the a over square root of e. Okay, and so you can see then that I'll call that tau, the lifetime. So then what you can see is that as the energy gets bigger, what happens to the lifetime? I'm asking you a question. As energy gets bigger, what happens to the lifetime? It gets smaller. That's right. And that makes perfect sense, because you see as the energy goes up, you can see how if the energy goes up, then you would have a smaller barrier, and you'd be able to get through more easily. And it turns out that this is a very famous relationship, and it actually explains the data. They actually got this, e to the 1 over square root of energy dependence, and so this was like a great triumph. So this was like a great, the first great nuclear physics triumph, where people really figured something out. So this is like a really famous problem, and people sometimes copy this technique to understand other things. Okay, folks, so that's all I want to say about alpha decay, but I think it's kind of cool. That's like the most famous example of WKB. It worked really well to explain that behavior. And so now I'm going to go to a new topic, and my new topic is the Dirac equation. Does anyone have any? Unless anyone has any last minute questions on alpha decay. Are you guys ready for Dirac? Dirac.
Yay. Yes.
Okay, so this is sort of like extra topics. So these are this is like the extra little topic at the end. I just want to say a little bit about the Dirac equation today, and on Thursday I'll say a little bit more. But the Dirac equation, let's talk about the Dirac equation. And so this is basically the first this was the first attempt to combine relativity and quantum mechanics, and it was successful. But the relativity is a special relativity. So this is how we combine special relativity and quantum mechanics, and it worked. How about general relativity and quantum mechanics? Did that work? No, that hasn't worked yet. So people haven't figured out how to do that yet. People are still working on that. But the special relativity in quantum mechanics, that was figured out by Dirac. And so Dirac did this. When the hell did he do it? I have it written down here. Does anybody remember when he did it? Dirac, when did he do it? Pretty sure it was in 1928. I didn't write it down in my notes, but I'm pretty sure that's when it was, 1928. Oh yeah, there it is, 1928. Okay, so okay, and the reason why this is significant is because when you do the Dirac equation, you get two things pop out of it. One thing that you get is spin. Spin just comes right out. It's like suddenly, boom, there's spin. It's like you combine relativity with quantum mechanics and boom, spin. Spin happens. You have to have spin. So that's quite beautiful and amazing. And the second thing is that you get antiparticles. And so this is really pretty amazing. And it's really quite cool to sort of see how this works, because the Dirac equation is based on just a very, very trivial, simple assumption. And you make this assumption and you just work through the details, and then boom, you get spin and you get antiparticles. And it's just extraordinary. And it's really one of the most amazing intellectual achievements ever. I mean, it's hard to think of a more amazing one than this. You know, it's like Dirac just said, hey, he just made some simple assumption and boom, he gets spin and antiparticles. And so that's pretty cool. And so that's what I want to, I mean, I'm not going to go through every detail, and it's pretty mathematical, and it's hard to, like, you know, gain intuition from it. I think it takes many years to gain intuition for the Dirac equation, but it's still fun and worthwhile just sort of going through the steps to see how you go from Dirac's initial assumption to spin and antiparticles. And so that's what I want to try to do. You know, sort of in like I'm going to, you know, skip some steps here and there, and it's pretty mathematical, I will warn you, but I think it's still worth it to see, because it's kind of like, you know, every step of the way is like, this is purely undergraduate physics. Some of the math is actually a little sophisticated, I think, but it's still kind of at like an undergraduate level, I think. And you'll see what I'm talking about. So, okay, so let's just do it. And so let's remember let's first remember non-relativistic physics, non-relativistic quantum mechanics, non-relativistic quantum mechanics. And let's just talk about free particles. Let's just focus on free particles, because that makes it simpler. I mean, you can also have confined particles, but let's just worry about free particles for now. And so quantum mechanics, for non-relativistic quantum mechanics, we have E is equal to P squared over 2M. And then what we do in quantum mechanics is we do E, we make an equation. We do this, we sort of go like this. We we multiply by the wave function, and we get E psi is equal to P squared over 2M psi. And then the E, we turn the E into an I H bar d dt, and we turn this thing, we do this trick where we say that P goes to H bar over I d dx. All right, that's basically the quantum mechanics trick. So I mean, I'm kind of, you know, oversimplifying it, but that's kind of it, you know. And then we get, and that then gives us the time-dependent Schrodinger equation. Which is I H bar d dt psi is equal to H psi. Okay, so that's our quantum mechanics. That's non-relativistic quantum mechanics. What, you know, in a nutshell, there it is. And you can, and so it's like we start with the classical. So we start with the classical expression. This is a classical expression. And then we do these little tricks, you know, and you're like, well, why do you do those tricks? Well, let's not get into that. You know, you learned that last semester, okay? But I'm just sort of reminding you, you know, if you were to like go to a very high level and just say, what the hell is quantum mechanics? Then this is what it is, okay? And so you look at it, you go, okay, that's quantum mechanics. We got it, you know. We just took the little E, turned it into an IH by ddt, and we took the P, turned it into ddx, and then we get this expression. And then for the free particle, we get this. IH bar ddt psi is equal to negative H bar squared over 2M d squared dx squared for in 1D psi. Okay, so that's our free particle Schrodinger equation that you all have seen many times, you know, and then you get psi is equal to, you know, e to the I k x minus vt, right? Or e to the I k x minus omega t. Okay, and so, you know, you have a traveling wave solution for the free particle. All right, so that's quantum mechanics, the non-relativistic free particle quantum mechanics. Now let's consider relativity. And when you look at this from a relativity point of view, something is screwed up about it. Can someone tell me what's screwed up?
We're like treating space and time kind of differently because we have a first time derivative and a second space derivative.
Very good. That's exactly right. So we could, you know, you can use various language. You can say it's not covariant. Time and space are treated differently. So that's one derivative. But here we have two derivatives. So we're treating time and space differently. That's right. And so for relativity tells us that we need to treat time and space on the same footing. We got to treat time and space the same. And so how do we fix it? Well, let's try to fix it. Try to fix. And so the most obvious thing is to do the whole thing again. Let's do the whole thing again. Let's go back to the classical physics, classical. And in classical physics, we have our new, including relativity, classical physics plus relativity, which is still classical. Then we get E squared is equal to P squared, C squared, plus M squared, C to the fourth. Right? So this replaces E equals P squared over 2M. So we got this new equation, which is better. It's bigger, better. It's the better version of P squared over 2M. Okay, it's my, you know, so you guys have all seen it? Did I get it right? That's 20 seconds. C squared, T squared. Yeah. Okay. And so if we start with this, then the obvious thing to do is to just do the whole thing over again. So just say, now multiply by psi, and then we get E squared psi is equal to P squared C squared plus M squared C to the fourth psi. Why not? That seems like a pretty reasonable quantum mechanics. And then this E squared will do the same thing. I H bar d dt, but now it's squared, right? And I'll just do the same thing here. That's going to be H bar over I d dx squared. So does this fix it? Does this fix it? Yes or no? I'm asking you a question.
Yes.
Yeah, it totally fixes it. This is great. Time and space are on equal footing. This is really good. And so this is called the Klein-Gordon equation. And it totally fixes it, right? Everything's looking really good. But then it turns out that there's a problem. There's a problem. The problem is that, and this is subtle, and I'm not going to dwell on this for too much, but I'll just tell you the problem, and you can look it up in a book somewhere if you want to learn more about it. But the problem is that it does not conserve probability. Does not conserve probability. And what do I mean by that? What I mean is that for quantum mechanics to work, we have to have a probabilistic interpretation of the wave function. We need to have probability is equal to psi star psi. Okay, we need to define a probability density, and then we need the probability to sort of be conserved. And what does probability conservation mean? Well, one way to formulate probability conservation is that we need the continuity equation to work. Continuity equation. And the continuity equation is this. D rho dt plus del dot j equals 0. And this would be a probability flux. Probability flux. And this would be probability density. Probability density. And this is getting a little into the details, but it's important, this is the reasoning. And this is basically just saying, what goes in must come out. What goes in must come out. That's the continuity equation. I know you've all seen it somewhere. You've seen the continuity equation. It's like whenever you have stuff like water, oil, blood, whatever stuff that's conserved, then anything that's conserved for conserved stuff. Anytime you have stuff that is conserved, and when I say conserved, I don't mean like energy conservation. What I really mean is like the conservation of the matter, the stuff. Like this like I start with a certain amount and I end up with the same amount a later time. I guess it's kind of like energy conservation, but I'm talking about like conservation of like water, blood, frogs, rain, stuff, matter. Then it has to satisfy the continuity equation. And probability is conserved, because I know that the integral of probability is 1. Probability is a conserved quantity, and so I can't create and or destroy probability. It has to be conserved. So in other words, like if the particle starts here, it has to go somewhere else. Probability is conserved, and so the bottom line is that the Klein-Gordon equation does not conserve probability. It does not satisfy this constraint. You cannot easily make it satisfy that constraint, and so we have to dump it. It turns out that in the real world, people actually use the Klein-Gordon equation. if you construct a field theory out of it, you can make it work. But, you know, that's pretty fancy, and that's like beyond, you know, what we're talking about here. So for our purposes, it failed. So we're stuck. So what is our Schrodinger equation going to be? What is our Schrodinger equation going to be? So we want, look, this is what we want. We want this, H psi equals E psi. This is what we want. We really like this, where we can turn the E into an IH bar ddt. So what we want then is we want IH bar ddt psi is equal to H psi. Now that's our familiar Schrodinger equation. We really like this, but what is the H? What is the H that satisfies relativity? What is it? So this was the conundrum. This was like really hot physics, you know, in the 20s, like, you know, 1925, and, you know, in the 20s, people were really wrestling with this. You know, they were really trying to figure out what the hell, what is the Hamiltonian that we can use that will allow us to construct a Schrodinger equation, a time-dependent Schrodinger equation, but we need that Hamiltonian to also satisfy relativity. And so Dirac is the guy who came up with the winning answer. And this is what Dirac said. Dirac said this, and it's just so funny, it's so simple. He said, let's assume, what Dirac said was, let's assume that the Hamiltonian is proportional to momentum. Linearly proportional. Linearly proportional. I guess proportional means linear, but I just want to make it even emphasize it. All he said is, let's assume that the Hamiltonian of a free particle is proportional to momentum. That's it. That is his assumption. And from that assumption, you get spin and antiparticles. That, I think, is the most amazing thing. It's like the completely trivial assumption, and yet it leads to all this fancy stuff. It's really quite beautiful and amazing. I mean, the Dirac equation is just extraordinary. That's it. That's all he said. And now, you know, and he got a Nobel Prize, and he's immortalized as one of the greatest intellectual achievements in the history of mankind. Just this, so simple. Hamiltonian is proportional to momentum. That's all he said. But it turns out that there's some, you know, work to do that. But so now let's do the details. It turns out that to say that the Hamiltonian is proportional to momentum is not as trivial as you might think. It is very simple, beautiful, intuitive concept. But to work out the math is non-trivial. You might think it's trivial, but it's not. And the mathematics is non-trivial to sort of take this assumption that the Hamiltonian is proportional to momentum and then figure out where it leads you to. To figure out where it leads you to is really quite non-trivial. And that's why Dirac, you know, so revered, because he's the person who did it first. And so let me explain what I'm talking about. So what Dirac said was, he said that if we make this assumption that the Hamiltonian is proportional to the momentum of a particle, then let's write the Hamiltonian in this special way. To get the units correct, he said, let's put a little c there, the speed of light, and let's create alpha. Alpha is basically just the proportionality constant. But to get all the units right and dimensions right, it's an operator, and it's going to dot the momentum, which is also an operator. But then let's add a constant, right? So it's just basically like a line, you know, it's slope times the variable plus a constant. And the constant will be beta, which is also an operator. And to get the units right, we'll multiply it by mc squared. Okay, and so this was his assumption, his ansatz, his assumption. So what Dirac did was he said, let's assume that the Hamiltonian has this this form, and then just follow it through and let's see if it works. And so the second thing is that it also must satisfy. He said, let's assume that the Hamiltonian has this form, but let's also assume that whatever we get must satisfy this idea that E squared equals P squared C squared plus M squared C to the fourth. And so if that's the Hamiltonian, then the Schrodinger equation must look like this. The new Schrodinger equation, which now of course we call the Dirac equation, but the new Schrodinger equation must look like this because we have, you know, E psi equals H psi, and so then where E we're going to replace with IH bar ddt, and so the new Schrodinger equation will be IH bar ddt psi is equal to, and now we have this the new Hamiltonian, C alpha dot P plus beta MC squared times psi, where this is H. Okay, so this is our new Schrodinger equation, and this was his assumption. And so to make sure that it satisfies this, so now, but here's the thing that Dirac, this is why Dirac is smarter than you or I, because Dirac said, let's assume that alpha and beta are completely general. Meaning, he said to himself, let's make no assumptions about the form of alpha and beta. The only assumptions are that they must satisfy the physical principles. And what are the physical principles? The physical principles that he knew are this. He knew that E squared equals P squared, C squared plus M squared C to the fourth. Nobody wants to fight that because classically we know that to be true. And we also know that the Hamiltonian must be Hermitian. So he kept the Hermitian. And Hermitian is important because he wanted the Hamiltonian to have orthonormal eigenstates and real eigenvalues. So, you know, the energy is real. So it's meaningful. So these are the only physical principles that he kept, that the Hamiltonian is Hermitian, and E squared equals P squared C squared plus M squared C to the fourth. Okay, so now the idea is, let's take these two physical principles and let's see what the consequences are. The consequences of these physical principles. Consequences. And I'll tell you right at the onset, the consequences of these physical principles is that we're going to get spin and we're going to get antiparticles, okay? But to see where that comes from is a little bit of work. So let's do that work. So let's start here. Start with this. H psi equals E psi, okay? Where this is going to be Dirac's Hamiltonian, his new Hamiltonian, and let's hit it again. Let's square it, because if I multiply it again, then I should get, if I hit it by H again, then I should get H squared psi is equal to E squared psi. Okay? Does that seem reasonable? So we just hit it twice, and so we should get H squared. So if H psi equals E psi, then H squared psi is equal to E squared psi. Okay, and so then he said, okay, well, if that's true, let's just expand this. Let's expand it. that was what he did. And so he did it like this. So 8 squared looks like this. It's going to be C alpha dot P plus beta MC squared psi is equal to P squared C squared plus M squared C to the 4th psi, since that's E squared. Okay, so I get this new equation. So, and this was Dirac who did this. He's like, okay, if this is true, then that must be true. Okay, so this was his next line of reasoning. And so then what he did was he just expanded this out. And so this is actually quite tedious to do, but let's do it anyways. So to expand this out, it looks like this. It's going to be, it's quite a mess, but you'll see what I mean. Because the dot product of alpha dot P, let's expand it out. So alpha dot P is going to be alpha x px plus alpha y py plus alpha z pz, right? Because alpha is a vector, you know, alpha is equal to alpha x hat plus alpha y hat plus alpha z hat, right? It has to be. It has to be a vector, because otherwise alpha dot P makes no sense. Plus beta MC squared. And now let's multiply it again times C alpha x px plus alpha y py plus alpha z pz plus beta MC squared is equal to psi. Okay? And so then now we have to multiply those two things. So you see why there's a lot of math here. So now, and this is what Dirac did. He just went through the math. He just kept going without making any assumptions about what alpha and beta are. So the whole point is that what we're trying to figure out is what is alpha and what is beta. That is the whole point of this exercise. And we will come to a conclusion. But it's messy. So now we got to multiply this, and you can see how there's 1, 2, 3, 4 times 4. There's gonna be 16 terms now. So, but let's write them down. And so it's c squared times alpha x squared px squared plus alpha y squared py squared plus alpha z squared pz squared plus c px py alpha x alpha y plus alpha y alpha x plus c squared px py no px pz alpha x alpha z plus alpha z alpha x plus c squared py pz py pz times alpha y alpha z plus alpha z alpha y plus mc cubed times px alpha x beta plus beta alpha x plus py alpha y beta plus beta alpha y plus pz alpha z beta plus beta alpha z plus beta squared m squared c to the 4. All right? Woo, look at all that. And this has to equal the other side of the equation, which is p squared c squared plus m squared c to the 4, right? Times, there's a psi that we're multiplying it by, so put the psi there. Psi, psi is equal to px squared, plus, c squared plus py squared c squared plus z squared c squared plus m squared c to the. Okay, so this is what you get, all right? And this was very tedious, but notice I'm just going through the algebra, all right? I'm not, it's nothing fancy, this is nothing, you know, you could do this too. So, but the thing is that what we have is that we see that this gigantic mess of all this stuff this gigantic mess of terms has to equal this smaller, much smaller mess of terms. How can I get these two things to be equal? They got to be equal, right? And so it turns out that this is a where, you know, alpha and beta are completely general mathematical operators, and so it turns out that if you're really smart and really good at math, then and Dirac was really smart and really good at math, and so Dirac realized that this is sort of a solvable mathematical system, and he realized that for this to be true, that this equation is true only if the following. What we need is alpha x squared is equal to alpha y squared is equal to alpha z squared is equal to beta squared is equal to the identity matrix, the identity operator, and at the same time you need that the anti-commutators alpha x, alpha y, and this is anti-commutator plus is equal to the anti-commutator of alpha y, alpha z is equal to the anti-commutator of alpha z, alpha x equals 0. And so that means the anti-commute. This is called anti-commuting. And you can see the anti-commutator right here, because see this, like right here, this expression, alpha x, alpha y, anti-commuter, is this expression, right? That's what the anti-commutator is. It's just the commutator, but with a plus instead of a minus. Where I'll just write it out. Alpha x, alpha y, anti-commutator is equal to alpha x, alpha y, plus alpha y, alpha x. So he realized that he needed all these anti-commutators to be 0. And you can see them in that expression. They're all over the place. And so if you set all those to equal to 0, then you have alpha x, beta equals alpha y, beta, the anti-commutator is equal to the anti-commutator of alpha z, beta. And you know, in hindsight, it's kind of obvious. You just look at those two expressions and you just say, how can these two expressions be equal? Well, the only one way is if this is true. You know, you need if these things are all true, then those two expressions are equal. And that was really the genius of Dirac, was to notice that. But then he went further and he said, okay, you know, what now I have, this is a constraint. This is the constraint then on alpha and beta. So what alpha and beta satisfy this constraint? What alpha and beta satisfy this constraint? And so what he figured out is that you need, if you take this constraint plus you say that alpha and beta are Hermitian, then the simplest solution, and there actually are more complex solutions, but the simplest solution is this, is that the simplest solution is that alpha and beta are four-dimensional matrices. And if you want to sort of see a derivation of that, you have to look at the book by Schiff. And there's another book by Bransden and Joachim. This is actually an undergraduate text, so I think this text is good. Bransden and Joachim. It's a quantum mechanics book by those people. And those books will sort of step you through the logic if you want to actually, understand why this is true. But I'm not going to get into it because it's a bunch of math. But it turns out that Dirac was really good at math. And so his genius was to notice that this is true. His genius was to look at these constraints and to realize that there is an operator that satisfies these constraints. I just laugh because I would have never figured this out in a million years. It's just so funny. And how could someone figure this out? But he did. He noticed that that there are a set of four-dimensional operators that satisfy these constraints. And now I will write them down because it's quite simple to do. Beta is equal to 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 0, 0, negative 1, 0, 0, negative 1. And alpha x is equal to 0, 0, 0, 1, 0, 0, 1, 0, 0, 1, 0, 0. And you see there is a pattern to it. And alpha y is equal to 0, 0, 0 minus I, 0, 0, I, 0, 0 minus I, 0, 0, and I, 0, 0, 0. And alpha z is equal to 0, 0, 1, 0, 0, 0, 0 minus 1, 1, 0, 0, 0, 0 minus 1. Okay, that's what he noticed. So this is the simplest solution to that. And these are 4x4 matrices. So these are the operators. And so then you'll notice a pattern that these are the polyspin matrices. So now you can start to see this is where spin comes from. So this is it, guys. This is where spin comes from. This is spin. It just happened. And so we can write it like this. We can say that beta, so shorthand is to say that beta is equal to I 0, 0 minus I. Alpha x is equal to 0 sigma x 0. Alpha y is equal to uh, 0 sigma y 0, and alpha z is equal to 0 sigma z 0. Where alpha, where sigma x, sigma y, sigma z are the polyspin matrices. And I, of course, is just the two-dimensional identity matrix. Okay. And so, okay, so now we go back to the Schrodinger equation, Pauli's new Schrodinger equation, and you see that we have H psi equals E psi is the new relativistic Schrodinger equation, but now we have, it looks like this, C alpha dot P plus beta MC squared psi is equal to E psi. And so then the question is, what the hell does my wave function have to look like? And we don't have time to go too much further, but I'll just say that if alpha and beta are 4x4 matrices, then what does the wave function have to be? The wave function has to be what?
A 4x1 matrix or vector.
Exactly. It has to be this 4-dimensional vector. And this is not a 4-vector, you know, like in relativity you have 4 vectors. This is not that. This is a 4-dimensional wave function. So you have these 4 dimensions. And I just want you to know that this is all just from math. You know, this has nothing to do with, like, you know, space, time, 4 dimensions, relativity. This is just purely looking at these constraints. This all comes from these mathematical constraints right here, where I'm putting 3 stars. So you're just working through those mathematical constraints, and then this has to be true. And so then you get alpha and beta are these 4-dimensional matrices, and if you plug them into the Hamiltonian and write down a Schrodinger equation, then you see that if alpha and beta are 4-dimensional matrices, then the wave function has to be 4-dimensional. Otherwise, the equation makes no sense, because I can't have this multiplying this unless the dimensions work out. Otherwise, the equation makes no sense. So it's like, you know, this was Dirac's reasoning, pure math. And so then the question for us is, what do these 4 dimensions mean? What do these 4 dimensions mean? And that was not obvious. But I will just tell you, this is, I will just tell you that these two, that's going to be the spin up positive energy solution. And this part is going to be the, this is going to be the spin up and spin down positive energy solutions. And these two here are going to be the spin up and spin down negative energy solutions. So we have negative energy. You have to have negative energy, which really kind of makes no sense. What the hell is negative energy? Because we're talking about kinetic energy. What the hell is negative kinetic energy? Negative kinetic energy solutions. Okay, but we will talk about this more next time. All right, so this is where we'll stop. But that's that.
Professor?
Yeah.
Will this be on the exam? I'm just kind of curious.
No, I'm not going to put,
All right.
I'm only going to put stuff on the exam that's from the homework. This will not
Okay.
be on the exam.
Okay.
Dirac equation, not on the exam. Okay.
And also that main psi function, that it would end up being a spinor, right? It would have spinor properties because it's a linear combination of
Yeah, that's
spin
right. It
states.
is a spinner, but it's a 4-dimensional spinner, not a 2-dimensional spinner. Like normally, you know, a spinner just has, you know, up and down, but this has like 4. So it's a really weird spinner.
Wow.
But
Okay.
it turns out that the wave function has positive energy components and negative energy components at the same time. Okay, and that's critical. Okay,
That's
it's a good place to stop. All right, guys. See you later.
Thank you.
Bye-bye.